Hi everyone, and welcome to this video on transformations of exponential functions. Now, in the past, we've seen a, k, c, and d. We've applied those to a number of different functions, and we're just going to take those same things and apply them to our base exponential function. Our base exponential function, however, is looking something like this. The only difference is, really, we could say it's the real base function is b to the x. The a value is going to be a vertical stretch or compression, but that is the starting value, and then b is 1 plus the growth rate, or 1 minus the growth rate, as we saw in yesterday's video, and then that's raised to the power of x. So if transformations are made to this function, here's how we write it. The x is shifted according to d, and then it is horizontally, so shifted left or right according to d, and it's horizontally stretched or compressed according to k. And remember that factor is 1 over k. We'll come back to that more in a minute. Then the a value is our initial value, and that's going to determine how much is vertically stretched or vertically compressed. And then the c value is going to shift it up or down. So let's just very quickly review these transformations. Like I said, they're exactly the same as they have been for our entire course. Nothing has changed. If there's the a value there, in general, we'd write it as a times f of x, where f of x, as I noted already, is b to the power of x. So then it's just written as a times b to the x. And so the a, if it's negative, is going to flip it over the x-axis. So if we had a function that looks something like this, then to flip it over the x-axis would do something like this. It's going to move all the values down. And then also, if a is bigger than 1, it's going to vertically stretch it. So if you have 2, it's going to vertically stretch. And if so for example, if we have 2, if a is a half, it's going to vertically compress it, right? Just as it always has. The next value that we have is the k value. And if we just applied the k value to the function, it would look like k times x in the exponent. And in general, we could write it as f of k to the x. We've seen that before when we just applied the k value to any general function. But to this specific function, we write it out like this here. If k is negative, it reflects over the y-axis. So in terms of a graph, what that would look like is if we had this function, it's going to flip it to look like this if k is negative. Also, if k is greater than 1, it's vertically compressed by a factor of 1 over k. So whatever the k value is, 1 over that is the vertical compression or stretch factor. So for example, if the k value is 2, it's going to compress it. And if the k value is a half, 1 divided by a half is 2, so it's going to vertically stretch it. It says vertical, but that's completely wrong. Let's correct that here. You'll notice in the handout I get you should be corrected already on that, but on this one it should say horizontal, horizontally compressed and horizontally stretched. So that's clear there. It's a horizontal stretch or compression for the k value. Also, for the c value, in general, we take the f of x value and we add a c value to it. And in this case, bx plus c, b to the power of x plus c. We know that if c is greater than 0, it's translated upwards. So for example, if it's 3, or for example, if it's negative 4, it's going to be shifted downwards that many units. And then the other thing we want to point out is d. And so remember the general form, it's x minus d. So if we have, for example, the equation y equals 2 to the power of x minus 3. That's going to translate to the right because the d value is positive. And then if we have a value or an equation of something like 2 to the power of x plus 3, that's the same thing as saying x minus negative 3. And so that would shift it to the left. So in general, we have this transformation, this function that would transform it according to all those transformations I just listed. So let's look at some cases and some examples of this. I want to first point out that the base function can be y equals 2x, 2 to the power of x, 3 to the power of x, or 1/2 to the power of x. So the first thing you need to do is figure out how you're going to graph that parent function. So you can make a table of values to graph the parent function. In the case of 2 to the power of x, you probably already know those values, 2, 4, 6, 8, 2, 4, 8, 16, 32, 64, etc. But in the case of 3 to the power of x, you could make a table of values. And let me just give you an example of what that might look like. If you were doing, you would use x values, I would start at least negative 2. And if you were doing the function f of x equals 3 to the power of x, then 3 to the power of negative 2 is 1 over 3 squared, which is 1 over 9. 3 to the power of negative 1 is 1 over 3, which is 1/3. Anything to the power of 0 is 1, and then 3 to the power of 1 is 3, and 3 to the power of 2 is 9. So you'd start with those 5 key points as your base parent function, and then you transform those according to a, k, d, and c. All right, so let's see if we can just identify the a, k, d, and c values of the following functions, and then write what the description of the parent function change would be. So in this first case, we just have 2 to the power of x plus 1. The only thing that's changed, the parent function is this y equals 2x, to the power of x. The only thing that's changed is that plus 1, which is the c value. The d value is 0. Careful with the a and k values. If they're not there, they're 1, because it hasn't vertically stretched or compressed. It hasn't horizontally stretched or compressed. Those are each going to be 1. If you write those as 0, then you're going to have 0 times 2 to the power of x, or you're going to have 2 to the power of 0x, which would make it not make sense anymore, and it wouldn't actually come to that form that the equation comes to. So what's the only change from the parent function? Well, it's shifted 1 unit up. Shifted 1 unit up. Well, what's the general form of how we're going to write this? Well, we're going to write this as y equals f of x, if we can get the pen working here, f of x plus 1. So that if the general function is f of x equals 2 to the power of x, then we replace the 2 to the power of x with f of x in general, and then it's plus 1. Go ahead and do that for the next one. I'm going to skip ahead to the third one, and then at the end of this, I'm going to show you all of them together, but I'm just going to do a couple here and then allow you to fill in the other ones. This next one, we have, again, the parent function of 2 to the power of x, and the only difference here is this value in front of it, which is the a value. The a value is 3. The k value, again, is 1, because there's no horizontal stretch or compression, so it has to stay as 1. And then the d value is 0, and the c value is also 0. So the only thing that happens, because there's only an a value, is that it is vertically stretched by a factor of 3. And then in general, if our parent function is f of x equals 2 to the x, as it was in the first case, then we can write this out as y equals f of x times 3. So we write the 3 right in front of the f of x. So 3 times 2 to the power of x, we're replacing 2 to the power of x with f of x, and that's our general form. So that if I gave you any single parent function for f of x, and I said that it was vertically stretched by a factor of 3, you could plug that parent function in and transform it using the same vertical stretch of that factor of 3. All right, let's jump ahead to the r of x now. In this case, the only thing that we have is there's no number there, but anytime you have no number, you can write a 1 there. So the a value is -1, and everything else is as normal. K value is 1, and the d and c values are both 0. So the only thing is that a value that's -1, which is a flipping or reflecting over the x-axis. It's the only thing that's happening there. And so we could write that in general. If f of x is equal to 2 to the x, in general we write that as y equals negative f of x. All right, and then s of x now. The only thing that we have here is this plus 1. And so the a value is 1, the k value is 1, the c value is 0. It hasn't been shifted up or down, but this is with the exponent. And so it's actually going to be a -1, because I said earlier that if you add it, it's the same thing as going minus or subtracting a negative. So in this particular case, we have a -1 as the d value. So the only thing that happens is it's shifted 1 unit left. Shift 1 unit left. And so in general, what that would look like is this. Y equals f of x plus 1, because it's the x that is being changed. So we need a change inside the brackets. So what I want you to do is fill in the other 4 rows and then compare your answers with me after you pause the video. So those are the answers that you should have got for the other ones that we didn't do. And I'll let you just pause the video if you need to and take those up. Now you'll notice we didn't do anything with the k yet, and so these last 3 examples are doing something with the k. The a value is going to be 1, the d and c are 0, but the k value in this first case is 2. And so remember that it's always a factor of 1 over k, so this is a horizontal compression by a factor of 1 over 2. And so how you would write this out in general is you would say y equals f of 2x. So go ahead, pause the video now, try the next 2, and then compare your answers with what I get. So there's the rest of that chart filled in. Now it asks 3 questions. The first question says, which of the above transformations affect the position of the graph's asymptote? Well, anytime we shift it up or down, that affects the asymptote, because as we know, for example, we know this for any function. If it's a positive base, it's going to get closer and closer to this line y equals 0, but never actually touch it. And so the value that changes that is the c value, because if you shift it up, that's going to bring the asymptote up. If you shift it down, it's going to bring the asymptote down. How can you find the equation of the asymptote of an exponential graph? Well, the equation of the asymptote is y equals the c value. If you need to convince yourself of that, go ahead and graph some of these functions using Desmos that we've seen above and just see how that affects things. The second question says the above exercise involved an exponential function where the base was 2. Would the results have been different if we used a different base? In other words, would the change from the parent function and the general form been different? No. Same transformations, and we would have had the same general function. Now, obviously, they would have looked different, but we would do the same things from the initial parent function. So the same transformations starting at a different parent function, but the same general function. The third question says, how would the graphs of y equals, or f of x equals 2 to the power of negative x and g of x equals 0.5x compare? Now you could go ahead and graph these, but I want to offer you just something that may be a little bit easier, and that is just to think about our exponent rules. If I told you something is to the power a negative power, we remember that we had this rule. We said a to the power of negative n is equal to 1 over a to the power of n. Well, it's the same thing that we can apply here. This is equal to 1 over 2 to the power of x. Well, how does that compare to 0.5x? Well, this is the same thing as writing g of x equals 1 over 2 to the power of x. Well, how could I simplify that? Well, I could simplify it. I could bring the x into both of these. 1 to the power of anything is 1. And then we have 2 to the power of x in the denominator. These are both the same. They look different, but they're both the same. They simplify using the exponent rules to the same thing. The last thing we're going to do now is graph using all these transformations. So let's do that below. So we have y equals negative 3 times 2 to the power of negative x plus 2 minus 1. And so you should be able to go through this and say, well, here's the a value. The k value is this value out in front of the brackets, because remember we have to factor the k out of the x and then the d value. And then the d value, keep in mind here that that's negative 2, because in general it's x minus 2. And the c value is equal to negative 1. So let's describe the transformations and graph this. We said the a value is negative 3. What's that going to do? It's going to do a vertical stretch by a factor of 3. And we also know it's going to flip it or reflect it over the x-axis. It would be really good of you to stop the video here if you think you have a good grasp on this, and try this out yourself and then check the answer after you've done this yourself. It's better for you to just try it out yourself than just watch me do it. So I encourage you, pause the video, give it a go. The k value is -1, and we know that's going to reflect it or flip it over the y-axis. The next thing that's going to happen is a d value of -2. We already noted why it had to be -2. And what's that going to do? It's going to shift it 2 units to the left. And last but not least, we have a c value of -1, which is going to shift 1 unit down. So what I'm going to do is I'm going to start by graphing the general function, which is y equals 2 to the power of x. I'm going to do that in green. Then I'm going to change colors to blue, and I'm going to graph this a value. I'm going to change colors to red, and I'm going to graph this k value. And then I'm going to change colors again, and in black I'm going to graph my final function, and these are going to be together with this d and c value. So that's the last thing I'm going to graph. So I'm going to graph all 4 of those graphs in the same grid and apply the transformations as I go through that. But you might be wondering, well, hold up, where do I start? So here's where you start. I noted already that you could start with a table of values, and we should always start with x values that go from -2 up to 2. We could do more than that, but you should at least do those. So that means the y values would be, remember the base function is y equals 2 to the power of x. So 2 to the power of -2, I'll do this first one off to the side just so you can see this. This would be equal to 2 to the power of -2, which is 1 over 2 squared. Well, that's 1 over 4. 2 to the power of -1 is 1 over 2. 2 to the power of 0, anything to the power of 0 is 1. 2 to the power of 1 is 2, and 2 to the power of 2 is 4. So those are the key points that I'm going to begin with before I do any stretching or compressing or transforming in any way. So -2, -1/4 is right there. 1 1/2 is right there. 0, 1, -1 1/2. Sorry, 1, 2, there we go, and 2, 4. So there's my initial graph. It's going to look something like this. You can continue that. 3 is going to be 8, etc. So this is the graph of y equals f of x. So then what we're going to do is we're applying the a value of -3, meaning we're going to vertically stretch it by a factor of 3. So 4 is going to become 12, but then we're also reflecting it over the x-axis. So 4 isn't just going to become 12, it's going to become -12. So the y value that was 4 comes to -12. We're keeping the x values the same because this is a vertical stretch or compression. So now the x value of 1, I have a y value of 2. I'm going to multiply that by -3 down to -6. 1 becomes -3. 1/2 becomes -3/2, and 1/4 becomes -3/4. And then my graph is going to look like this. This is the function y equals -3 times f of x. So now what I'm going to do in red is I'm going to apply the k value. And the k value is only going to reflect it over the y-axis. It wasn't any horizontal stretch or compression. So I take all these values and I reflect them over the y-axis. So I'm keeping the y values the same and I'm changing the x values, like so. And I could make this -12 down here as well. And then I'm going to graph through all of those something that looks like, if it doesn't jump on me here, something that looks like that. So this is the graph of y equals -3 f of -x, the k value being -1. And finally, we'll go ahead and we'll graph the final result. We're going to shift this whole red function over 2 to the left and down 1. So we're going to take every one of these points, go over 2, down 1. Over 2, down 1. Over 2, down 1. And eventually, I'm going to arrive at is something that looks like this. Now, there's one thing we need to indicate before we draw a curve through that, and that is this. We know that the original function had an asymptote at y equals 0. But this function does not have an asymptote at y equals 0 because we've shifted it down by 1. We said that earlier. We said that y has to equal the c value. So this particular one, now that we've transformed it, has an asymptote at y equals -1. And so when we go to draw the curve, we need to not cross that asymptote. We get closer and closer to it, but we never cross it. It's hard to draw sometimes and get it really accurately, but there it's going to look something like that. This is the graph of y equals -3, f of negative x plus 2 minus 1. That's the general form of that graph. There you go. If you have any questions, as always, reach out for help. All the best, and that's a wrap, ladies and gentlemen.